everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 7 Sound. We will be discussing about reflection of sound waves and echoes. Are you ready for this class? Let's start. What is sound? Here you can see a housefly. While you're resting or you're sleeping, you may be hearing the sound of a housefly and you feel very disturbed. Okay, a mosquito which is moving around you and making a noise. You can hear it, right? Yes. So you will be hitting the mosquito to kill it. Okay, you're making a sound there. You're hitting it, you're making a sound. I have a glass and spoon. When I'm hitting this glass, you can see that sound is produced. I'm speaking. When I'm speaking, you can hear me, right? So I am producing sound. So all these cases, there is some vibrations happening and this vibrations is producing sound. Okay, so we can define sound. Sound is a form of energy. Sound is a form of energy which gives us the sensation of hearing. So here we are hearing the sound and sound is being produced due to vibrations and it is a form of energy. Now, how do we hear sound? We have said how sound is being produced. I am speaking, I am producing sound. So here in this case, there are two important people, okay? One is the source of sound. Here we have a radio. This radio is producing sound. If I am speaking, I am producing sound. So I am the source, okay? So if you have a musical instrument, then the musical instrument will be the source, okay? From the source here, you can see a person is hearing the sound. Okay, this person who is hearing the sound is the receiver. Okay, so you have a source and a receiver. These two are very important. Now the sound should travel from here to here. Yes, to travel from here to here, it should travel through a medium. There should be a medium. If there is a medium, only through this medium, sound can travel from this radio and reach this person and he can hear the sound. So, three important things: source, medium and receiver. Okay, the sound wave cannot travel through vacuum. There should be a medium. Either it can be a solid, it can be a liquid or it can be a gas. When you are at smaller classes, you might have done this. On the bench, on the desk, you will be lying on one side and your friend will be tapping on the other side. You will be able to hear the sound, which means through that wooden bench or a metal bench, what is happening? The sound waves are traveling. It is creating vibrations and the waves are traveling, right? And you are able to hear the sound. Okay, sound travels through water, sound travels through gases. If I am speaking and you are able to hear me, which means through gas, sound can travel. Okay, so here you will understand one thing, vibrations are created in the source and that vibrations travel through the medium and reach the person. So you can say that a vibrating body causes vibrations in the particles of the surrounding medium which travel in the form of waves with a certain speed. Okay. Now in this case, when I am tapping this glass, what is happening? When I am tapping this glass with a spoon, what is happening? Vibrations are created and I can feel the vibration with my hands. Okay, so these vibrations are traveling through the air medium and me and you are able to hear it. Okay, frequencies of sound wave. As we have said, vibrating body creates vibration in the medium and we are able to hear the sound with our ears. Okay, our ears can hear sound waves only which is in a particular range of frequencies. So this is called the audible range of frequency, human audible range. Okay, this human audible range is from 20 Hertz to 20 kilohertz or 20,000 Hertz. So this is the audible range of frequency. Okay, below 20 Hertz and above 20,000 Hertz, you won't be able to hear. It is normally human beings. For human beings, it is. For other organisms, it may be different. Okay. For human beings, our audible range is 20 Hertz to 20,000 Hertz or 20 kilohertz. So, this region, that is sound waves of frequency below 20 Hertz are called infrasound or infrasonic sound. Okay. Infrasonic sound waves. Okay. And frequencies above, that is sound waves of frequencies above 20 kilohertz is called ultrasound or ultrasonic sound. Ultrasonic sound waves. Both these we won't be able to hear. Okay, only the hearing audible range will be 20 hertz to 20 kilohertz. So when a person gets older, there will be change in this frequency. It will be the audible range will be decreasing. Okay, all these waves, let it be the infrasonic, the normal audible range or ultrasonic frequency sound waves, all of them travel through a medium with the same speed. Okay, but the frequencies will be different. Clear? We have said that sound waves need a medium to travel. Sound waves cannot travel through vacuum. So when you take the case of sound waves, it is very fast in case of solid. So in solid, sound can travel faster because all the particles are closely packed. Okay, they are close to each other and the vibration will be easier. Then it is, when it comes to the case of liquids, it is slower, and when it comes to gases, it is more slower. Okay, so we have said that sound waves can travel through a medium. Now here what is happening? Due to the vibration, there is kinetic energy created, and this kinetic energy will be converted into potential energy. So that we can say that sound waves are elastic waves or sound waves are mechanical waves. What is mechanical waves? We have studied about mechanical energy, kinetic energy and potential energy are the two different types of mechanical energy. Similarly, you are having mechanical waves, and sound wave is an example of a mechanical wave. Now what are mechanical waves? The mechanical waves are of two types, longitudinal waves and transverse wave. This is how a longitudinal wave looks like, and this is how a transverse wave looks like. Okay, so we'll explain this in detail. What are longitudinal waves and transverse waves? Just look at this figures. So here you have a longitudinal wave and this is a transverse wave. So in case of longitudinal waves, the particles of the medium will be moving in the same direction of the propagation of wave, the direction of propagation of wave. Then it is called a longitudinal waves. So here compressions and rarefactions will be produced. When you take a spring, okay, when you take a spring, you press it and leave it, what happens? You will be getting compressions and rarefactions. Okay, so here in spring, this is how you will be getting. So this is an example of longitudinal waves. Okay, here compressions and rarefactions you can see. When the particles of the medium, it will be in the region of compression, it will be very closely. The particles will be very close. When it comes to the region of rarefaction, it will be at distances. Again compression, it will be very close. Again rarefaction, it will be at a distances. Okay. Now what about transverse wave? Here you can see on the surface of water. If you put a stone, you can see waves in this way. So here what happens is the particles of the medium will be traveling in a direction that is perpendicular to the direction of propagation of wave or normal to the direction of propagation of wave. So in this case, crust and trough will be formed. So this is how a wave look like. For example, you take a string. Okay, you hold the string and strike it at one region. You can see this is how the waves will be formed. So here you will be having crust and this is your trough. You can see that the particles are moving perpendicular. This is how up and down the particles will be moving. But here the wave is moving in this direction. Okay, perpendicular to the direction of motion of the particle. So we can define longitudinal waves if the vibrations of medium particles are along the direction of propagation of the wave, thus forming compressions and rarefaction in the medium. The wave is called a longitudinal wave. If the medium particles vibrate normal to the direction of propagation of the wave, forming crust and trough, the wave is called transverse wave. For example, if you take the longitudinal waves will be formed in all three states, that is solid. Either it can be in the solid state, in liquid state and in the gaseous state. But when it comes to the case of transverse wave will be seen only in solids and on the surface of water. Okay, only in these two cases you can see transverse waves. This is the basic differences between longitudinal waves and transverse waves. Now we will be defining some basic terms that we need to solve problems in this chapter. The first one is amplitude. So here you can see a wave. What is amplitude? Amplitude is nothing but the maximum displacement. So this is a mean position. Okay, this is your mean position. From this mean position you can see that in both the direction the wave is traveling. Okay, the maximum distance or maximum displacement is called the amplitude. So wave can be like this, like this, like this, like this. Okay, and this is the maximum it can go. And this maximum displacement is called the amplitude of the wave. Okay, so we can define amplitude, which is represented by small letter a, the maximum displacement of the particle of the medium on either side of its mean position, and the straight line path is a mean position. Second is time period. Time period is the time taken by the particle of the medium to complete its one vibration. One vibration means it starts from here till here. This is one complete vibration. From here to here, it is the second vibration. So it is nothing but the time period is the time taken to complete this vibration. One complete vibration, what is the time taken is the time period. Next is frequency. The number of vibrations made by the particles of the medium in 1 second, or you can say, if you consider a point, number of waves that is passing through that point in 1 second is the frequency, which is represented by F. Okay. Next is wave velocity. We know that speed is equal to distance by time, or velocity is equal to displacement by time. So here the distance travelled in 1 second is called the wave velocity, represented by capital V. The distance travelled by the wave in 1 second. And the fifth one and the final one, that is wavelength. What is wavelength? Here you can see 2 consecutive crusts. This is 2 consecutive troughs. So the straight line distance between 2 consecutive crust or 2 consecutive trough is called the wavelength, which is represented by lambda, the distance travelled by a wave in one time period of vibration of the particle of the medium. Clear? So this is what wavelength is. Now we will be studying a relation between wave velocity, wavelength and frequency. We have wave velocity V is equal to wavelength lambda into frequency F. So this is a relation. Okay, we have another relation between frequency and time period. Frequency is 1 by time period, which means when time period decreases, frequency increases. Also, we know that this lambda and frequency are also inversely proportional. Lambda is inversely proportional to frequency. When frequency increases, wavelength decreases. When wavelength increases, frequency decreases. Okay, velocity of longitudinal waves in gaseous medium. If you are considering a gas whose density is D, pressure is P and the ratio of specific heats is gamma, then you will be having velocity V is equal to root of gamma P divided by D. Okay, in case of air, the ratio of specific heats gamma is equal to 1.4. Okay, now here you can see that velocity is inversely proportional to the density. Root of density. Okay, which means when you increase the temperature, if you are increasing the temperature or the humidity of the gas is increasing, if the humidity is increasing, in both these cases density, what happens is the density will decrease. Okay, density will decrease. What happens to velocity when density decreases? When density decreases, velocity will increase. So velocity of the wave, sound wave, will increase when there is a decrease in density. So if you are changing the pressure, due to this change in density, there won't be any change in pressure. That means any change in pressure cannot make a change in the velocity, because it is dependent. There is a change in density already that is made because of temperature and humidity. Density will be changing and change of pressure is not to be considered. Then you will be getting the velocity to be increasing. Okay, if density decreases, velocity increases. Speed of transverse wave in a stretched string. When you take the case of a stretched string, if it is a loose string, the sound waves produced will be of less amplitude. But when you have a stretched string and you are trying to vibrate it, the string's vibration, the energy will be more and there the sound produced will be more. So the relation is, velocity V is equal to root of T by M. So here when you consider loose string and a stretched string, the tension will be more in case of a stretched string. So when tension increases, velocity also increases. Okay, the speed also increases. Then the second is, this is M is not mass, M is the mass per unit length. Mass per unit length is the M. Okay, so when mass per unit length decreases, the speed will, or the speed of sound waves in a stretched string will be increasing. This is the two things on which the speed of sound waves in a stretched string depends. One is tension and the second is mass per unit length. Difference between light and sound waves. We know what are light waves and what are sound waves. First you take the light waves. These light waves are electromagnetic waves. Though this electromagnetic, we have studied about the electromagnetic waves, different types of electromagnetic waves, gamma rays, X-rays, then microwaves. All these are electromagnetic waves. So one of the light waves are an electromagnetic wave, but when it comes to the case of sound waves, these are mechanical waves. Second point, they can travel in vacuum. Can sound waves travel in vacuum? In case of sound waves, there should always be a material medium to transfer the wave. Okay, it should either travel to a air, water, or that is a gas, liquid or a solid. Medium should be there for the traveling, but it cannot travel through vacuum. Third point, the speed of light waves is very high. It is of the range 3 into 10 raised to 8 meter per second. C is equal to 3 into 10 raised to 8 meter per second. The speed of sound wave is very low compared to the speed of light waves, and it's of the range 330 meter per second. Sometimes it may be 320 meter per second, or it can be 340 meter per second, depends on the value that is given in your textbook. So normally we take 330 meter per second, and it is different in different mediums. So in air, it is very low, which is 330 meter per second. When you take in the case of sea water there, it will be 1400 meter per second. When you take the case of steel, it is 1600 meter per second. So it is different for different mediums. Okay. Next, the wavelength of light waves visible is very small, of the order of 10 raised to minus 6 meters. Okay. When you take the wavelength of the light waves, it is of the range 10 raised to minus 6 meters. But when it comes to the case of sound waves, it is 10 raised to minus 2 meter to 10 meter. So this is the range. You can calculate it with the frequency known. You know, frequency is of the range 20 hertz to 20,000 or 20 kilohertz in case of humans. Okay. With this, you can calculate the wavelengths. Okay. Next, the final one. These waves are transverse wave. Light waves are transverse wave. When you take the case of sound waves, we have said that sound waves are both longitudinal waves and transverse waves. In case of air, it is always a longitudinal waves. We have said this before. So longitudinal waves in case of solids, liquids and gases, the sound waves are longitudinal waves. Transverse waves are, sound waves are transverse waves only in case of a solid and on the surface of a liquid, surface of water. Okay. A reflection of sound waves. When you take a surface, that is, you can take a hard surface or mirror, you know that the light waves gets reflected. You have studied the laws of reflection. There will be a normal. This is your incident ray. Light ray is incident on the surface. This is a point of incidence. From here, the light ray gets reflected. This is your incident ray. And this is your reflected ray. Here you have a normal. At this point of incidence, you will be having angle of incidence, angle of reflection. So, what are the laws of reflection? First law, angle of incidence will be equal to the angle of reflection. Second, the incident ray, reflected ray and normal at the point of incident all lie on the same plane. Both these laws are also obeyed by the reflection of light. Even in case of light, when it strikes a hard surface or some surface, what happens, or a sharp surface, what happens is the incident sound wave will get reflected. There will be angle of incidence and angle of reflection. Okay. For example, let's take the case, you have a surface here. Okay. From here, you are sitting here and you are producing a sound. Okay. Through a cardboard, let's say with a cardboard or with a paper roll, you are making some tube. Okay. You are making a tube. And your friend is sitting here and he is going to hear you. Okay. So what happens is the sound waves that you are sending, he will be able to hear the sound waves. Okay. Through this, the sound wave is traveling. Here you will be having incident sound waves angle and the reflected angles. Okay. So this is what the reflection of sound wave is. The return of sound wave on striking a surface like wall, metal sheet, etc. back in the same medium. So this can be observed. For example, here you have a wall. And this boy, you can see he is shouting. Okay. After shouting, what happens? It goes and hits the wall and comes back. Okay. The waves are coming back, which means here there is a rebounding or reflecting of sound waves. So this is reflection of sound waves. Reflection of sound waves. We know the reflection of light. When light rays falls on a smooth surface, reflection will take place and you will be able to see the image. So this reflection is a regular reflection. Okay. Then this case, that is when you have a rough surface or a hard surface, there what happens is the reflection is a diffused reflection. Okay. There you won't be able to see the image properly because light rays are getting reflected in different directions. Here you can see that all the reflected rays are parallel to each other and hence the image will be formed. In this case, image won't be formed. This is a case of light rays. But when it comes to the case of sound waves, in this case, reflection, diffuse reflection can also happen, but here what happens is, only the difference will be that there will be a reduce in the loudness. The sound waves, there will be a reduction in the loudness of the sound. Still, it will be audible. If, for example, if the rays are falling on the surface, let's say on the rough surface, here what happens is you can see when you draw a normal, reflection is still happening, but the normal will be different in these cases and therefore the rays won't be parallel to each other. Since they are getting reflected or scattered in different directions, due to this reason, you will be still able to hear the sound. The only difference is that the intensity or the loudness will be reduced. Okay, let's say if 100% of sound waves are falling, only a 90% loudness will be heard. Okay, and this 10% will be absorbed by the surface due to this roughness. Okay. So you can say the points, important points is reflection of light requires smooth and shining surface like mirror. But when it comes to the case of a sound wave, it is not necessary that you have a shining surface or a smooth surface. Still it will happen. Only one requirement or one condition is that the surface on which the reflection is happening should be having a size which is greater than the wavelength of the light that wavelength of the sound wave that is falling on it. Okay, the size of the surface should be, the size of the material through which this is going to happen, the reflection is going to happen, should be having a size which is greater than the wavelength of the wavelength of the sound wave that is falling on it. Echo. You all know what echo is, right? You go on top of a mountain or you go in a forest and shout your name. What happens? You will be able to hear your name multiple times, right? So this reflection, this is happening due to reflection of sound waves, and this is called an echo. So you can define echo as the sound heard after reflection from a distant obstacle such as cliff, a hillside, wall of a building, edge of forest, etc. after the original sound has ceased is called an echo. Now you have to remember there will be two sounds. The first is the original sound or the normal sound. Okay, here original sound will be there and there will be the reflected sound. Okay, so this is the original sound. Here you can see the original sound is going and hitting, the waves are going and hitting a wall. What happens? You can see the reflected sound. So in case of echo, you will be able to hear it multiple times. Now you can calculate the speed. Here you have to see that the distance between this person and the wall, let's take it as d. D is the distance between them. Okay, to hear an echo or an echo to happen, the wave should travel from here to here and come back to the person or come back to the source. Yes, the total distance means here if you are taking the distance between these two objects as d, then the total distance travelled will be equal to 2d. So in order to calculate the average speed, if you have to calculate the average speed of sound v, we need to know the total distance that is travelled. Total distance travelled will be 2d in this case. That is 2d divided by time taken t. Okay, how much time is taken to hear the echo? Okay, 2d divided by t. Now from this you can also calculate what t is. How to calculate t? T will be equal to 2d divided by v. If you know speed, average speed and time, then you can calculate d. The distance between the source and the obstacle. How can you calculate? D will be equal to Vt divided by 2. Okay. Now, in case of air, we know the speed of sound. What is the speed of sound? It is equal to 340 meter per second. Okay. Now, what you have to remember is the time taken. You know that if you see an object, it will persist in your eyes for some time. You will be able to remember that object for some time, right? Similarly, the sound can stay in your ears for some time, and this is 0.1 seconds. That is, when you hear the original sound and the echo, the time between them should at least be 0.1 second, or else it cannot be called an echo. If you are hearing the sound, the reflecting sound along with the original sound, or without a time interval of 0.1 second, then it is not an echo. The time interval should be at least 0.1 second, only then you can call it an echo. You can distinctly hear the original sound and the reflected sound, or else it will be getting superimposed and you won't be able to hear the echo clearly. If the time interval is at least 0.1 second, then you will be able to hear it clearly. Okay, so here if you are taking time as 0.1 second, the minimum time as 0.1 second, t is equal to 0.1 seconds, and in that case you can calculate d. D will be equal to, what will be d? D will be equal to 340 into 0.1 divided by 2. 340 into 0.1 is 34 divided by 2, which is equal to 17 meter. So what do you understand? In order to hear echo, the distance with the minimum distance between the person and the obstacle. Here we have a wall. Okay, the minimum distance should be 17 meter. If the distance between the person and the obstacle is less than 17 meter, then the echo cannot be heard. Okay, then echo won't be here. You won't be able to hear the echo. So got an idea about what echo is? We have experienced echo many times. So this is an explanation for it. Now when do we hear an echo, or the condition for hearing an echo? An echo is heard only if the distance of the person producing a sound from the rigid obstacle is far enough to allow the reflected sound to reach the person at least 0.1 seconds after the original sound is heard. This I have said you before. Here, if you have a person and a wall, then the distance between them should be far enough, okay, and we have calculated the distance. So only if they are far enough, only then at least there will be a time interval of 0.1 second and the person will be able to hear the echo distinctly. So first point is the minimum distance between the source of sound or observer and the reflector is in air must be 17 meters. This is calculated in case of air. If you are calculating it in the case of water or in case of steel, there the velocity will be changing, speed will be changing, and therefore the minimum distance will also be changing. Okay, for example, if you take the case of water, so let's say in the case of sea water, the speed is 1400 meter per second. V is equal to 1400 meter per second. Then the time, it is 0.1 second itself. Then what is the distance? Distance d will be equal to Vt divided by 2. V is equal to 1400 into 0.1 divided by 2. 140 divided by 2, which is equal to 70 meter. The distance between the observer and the obstacle should be at least 70 meter. Only then the echo can be heard. Now the second point, the size of the reflector must be large enough as compared to the wavelength of the sound wave. This we have discussed when we have explained about the reflection of sound waves. The same point, the size of the reflector or the obstacle should be large enough. That is, it should be more than the wavelength of sound wave that we are using. The third point, the intensity of sound should be such that the reflected sound reaching the ear is sufficiently loud to be audible. If you go on top of a mountain and in a very small intensity, if you are shouting or if you are making a sound or you are saying a name at a very small intensity or a very low voice or low voice, what happens? You won't be able to hear the echo. The intensity should be high. Only then it can reach the obstacle and gets reflected back. Clear? Reverberation. Reverberation is something that is different from echo. We have said that to hear an echo, the time interval should be at least 0.1 or above 0.1. If the time interval between the sound waves, that is a reflected wave, reflected sound and the original sound is less than 0.1 second, in that case, we are going to hear the reverberation. That is, you consider a room. Inside the room, so a person is speaking here. There are multiple reflections happening. So you can see the direct sound waves or sound paths and the reflected paths. Okay, this reflected paths, what happens? It undergoes multiple reflection. In the wall, it can strike the next wall and strike here. From here again, it goes up. It can strike here. So this continuous reflections of sound wave is happening, and then the sound here heard will be a loud voice, not an echo. So here this sound is called, this phenomenon is called reverberation. You can see it in the case of a big auditorium or in case of a theatre. In all these cases, what is happening is the sound produced, the sound that comes from the source is undergoing multiple reflections. Okay, so in case of an auditorium or in case of a theatre, you can see that sound absorbing material on the roof, then seat, all these are made up of sound absorbing material in order to prevent this reverberation. This excessive sound, the disturbance can be prevented using fibers that can absorb the sound waves, okay, absorb the reflected sound. Determination of speed of sound by the method of echo. So, the echo method can be used to determine the speed of sound. Let's see how. This is a simple experiment. Let us take the observer and the wall or the reflector is at a non-distance. You know the distance, let's say at 50 meter distance. So, observer and reflector is at a distance of 50 meter. The distance between them is 50 meter. That is, we are taking a non-distance. From here, the observer is shouting or producing a sound in order to hear the echo. So, we know the distance in this case. We know to find the speed, right? Speed V is equal to 2D divided by T. Now, how to get the time? Here, we have taken the non-distance to calculate the speed. Okay, so you can calculate what 2D is. To get the time here during this experiment, you are using a stopwatch of at least 0.01 second least count. Okay, 0.01 second least count stopwatch you are using. Then you will have to calculate. That is, echo will be heard in some time. Yes, how much time it has taken to hear the echo from the time when the sound is produced. That time is noted and then V is calculated. Okay, so first you will be performing this experiment. You will be getting a value V is equal to 2D divided by T. Okay, you will be getting some value. Again, the experiment is performed to get more accurate results. Again, the experiment is performed in the same way, noted the value. Again, performed, noted the value. So, different V values you will be getting. V1, V2, V3, V4, V5. So, to get the most accurate result, what you will do is, you will take the average of these. Okay, after performing, that is how you do physics experiments, right? So, you will be performing the experiment many times and take the average value. Okay, so this is how you can find the, or you can determine the speed of sound by using the echo method. Clear? Now, what are the uses of echo? Where does echo find application? Echoes find their application in the sound ranging and echo depth sounding by using ultrasonic waves. What are ultrasonic waves? Of frequencies above 20,000 Hertz or 20 kilohertz. Sound waves of frequency above 20,000 Hertz or 20 kilohertz is called ultrasonic sound. So, this ultrasonic waves can be used, that is for to understand the applications of echo. The first is properties. What are the important properties of ultrasonic waves? First one, they can travel undeviated through a long distance. That is along the same path because of this high frequency. They can travel along the same path for a longer period of time. Okay. Second point, they can be confined to a narrow beam. That you can get very narrow beams of these ultrasonic waves. Third, they are not easily absorbed in a medium. What happens if sound waves are absorbed? The loudness or the intensity will decrease. So, these waves cannot be absorbed easily. That is, a medium cannot absorb these waves easily. Use of echo by bats, dolphins and fishermen. We know the audible range of frequency of humans, that is 20 Hertz to 20 kilohertz. But when you take the case of other animals, bats, dolphins, dogs, etc., they have a higher audible range. That is, in case of bats, they can detect and transmit rays or the ultrasonic rays of frequency 100 kilohertz. Okay, frequency 100 kilohertz waves they can produce. So, here in case of bats, what is happening? You can see here we have an insect. These bats, they will be sending ultrasonic waves. Okay, you can see big ears in there. Okay, now what happens is these waves go touch the insect, that strikes the obstacle, here the insect, and comes back. So, they will be able to calculate at what distance the insect is. Okay, they will know at what distance, because in the dark, in most cases we know that the bats will be coming out during the night time. So, in the dark, even in the dark time, they are able, that is during the dark night, they are able to detect the insect. Same happens in case of dolphins. Here you can see these dolphins are sending ultrasonic rays. These ultrasonic waves, they go strike the obstacle. Here we have fishes and then come back, and the dolphins will be able to calculate what distance their prey is. Okay, even in the case of fishermen, here what they are doing is, the fisherman will be sending ultrasonic sound waves from a source, and these sound waves, what happens is, they go strike the fish and it comes back. Okay, they go strikes the fishes, and what happens is, there will be a detector and they can calculate at what distance the fish is. Clear? So, this is a use of ultrasonic sound waves. Use of echoes in medical field. You might be heard about ultrasonography, echocardiography. In all these cases, what is happening is ultrasonic sound waves are sent, and these will be able to, using these sound waves, will be getting the image of, that is, you can get the images of your heart, your internal organs. So, for this purpose, that is, even the scanning process, you can see from the mother's womb to see the baby, how the baby is moving. All these can be seen, how much the growth the baby has. All these scanning, ultrasonic sound waves will be used. Let us take an example. The human ear can detect sound in the frequency range 20 Hertz to 20,000 Hertz. If speed of sound is 330 meter per second, find the wavelength corresponding to the audible range of frequencies. So, what is the relation between wavelength and frequency? We have speed of sound is equal to frequency into wavelength, where lambda is wavelength and f is the frequency. Here minimum frequency is given, f min is equal to 20 Hertz, and maximum frequency is given, f max is equal to 20,000 Hertz. Okay, then speed of sound is 330 meter per second. First, we will be finding the maximum frequency. From this relation, we will be having frequency is equal to V by lambda, or lambda is equal to V by F, which means lambda and frequency are inversely proportional. That is, when frequency increases, wavelength decreases. For minimum frequency, wavelength will be maximum. So, when we have minimum frequency, the wavelength should be maximum. So, first we will find wavelength maximum, lambda maximum. How to find? Lambda is equal to V by F. Here V is 330 divided by minimum frequency is 20. 33 divided by 2, 16.5, and the unit of wavelength, it will be meter. Okay. Now next we'll find the minimum wavelength, which is equal to, again, the speed 330 divided by, here the maximum frequency is 20,000 hertz. Okay, which is equal to, here you can cancel 1 0. We have 33 divided by 2 is equal to 16.5. Here we have 3 zeros, which means into 10 raised to minus 3 meters. 10 raised to minus 3 meters, you can convert and write 16.5 millimeter. Okay. So, lambda max and lambda min, that is a wavelength corresponding to the maximum and minimum frequency we have obtained. Example 2. A sound produced on the surface of a lake takes 4.5 seconds to reach a boatman. How much time will it take to reach a diver inside water at the same distance if speed of sound in water is 4.5 times the speed of sound in air? Given that speed of sound in water, V in water, is equal to 4.5 into V in air, speed of sound in air, which means V in water, the speed of sound in water, divided by speed of sound in air will be equal to 4.5. Okay, what else is given? A sound produced on the surface of a lake takes 4.5 seconds to reach a boatman, which means the time taken in air is given. On the surface of lake means the time taken to travel, sound to travel in air. T in air is given, which is 4.5 seconds. And we have to find how much time will it take to reach a diver inside water. Means the time taken in water we have to find. Okay, we have, that is, the distance traveled will anyways be the same. It is given that the distance is same distance. Okay, which means V in water will be equal to 2D divided by time T in water. Okay, V in air will be equal to 2D divided by time in air. This is first equation, this is second equation. Now dividing 1 and 2. Okay, when you divide 1 and 2, what happens? V water by V air is equal to 2D divided by T water divided by 2D divided by T air, or V water by V air is equal to 2D divided by time taken in water into time taken in air divided by 2D. What you are doing? You are taking reciprocal and multiplying. 2D can be cancelled. Okay, total distance travel can be cancelled. You know the value of T in water. Sorry, you know the value of T in air. You have to find the T in water. Right? So, what is this value? V in water divided by V in air we have calculated, which is 4.5. 4.5 is equal to T in air is also 4.5 divided by T in water. Okay. Therefore, time taken in water is equal to crossing. We get 4.5 divided by 4.5, which is equal to 1 seconds. Okay. 1 second is the time taken. Clear? Example 3. A boy stands 60 meters in front of a tall wall and claps. The boy continues to clap every time an echo is heard. Another boy finds that the time taken between the first and 51st clap is 18 seconds. Calculate the speed of sound. So, here you have a boy who is standing in front of a tall wall. Distance between them is 60 meters. Then what is the total distance travelled? The distance is 60 meters. So, total distance travelled 2D will be equal to 2 into 60 meters, which is 120 meters. Okay, 120 meters. This is the total distance traveled. What is given? It is given that the boy continues to clap every time an echo is heard. Another boy finds that the time taken between first and 51st clap is 18 seconds. What does it mean? The time interval between the first and 51st clap is 18 seconds. Okay. Time interval between first and 51st clap is equal to 18 seconds. Then what is the time interval between first clap and second clap, or between second and third clap? That is, when you consider two successive claps, what will be the time interval? Total there are 50 claps from first to 51st. There are 50 claps. Yes. Therefore, the time interval between first and the second clap, or two successive claps, will be equal to total time taken divided by number of claps, that is 18 seconds divided by 50. 18 seconds divided by 50. Okay, therefore this will be the time taken to hear an echo. How is an echo heard? That is, total distance traveled will be from here to here, back to here. Okay, only then one echo will be there. So therefore, that is between two successive claps. He is clapping when the first echo is heard, right? So that time interval be the time taken to hear an echo. Therefore, time taken to hear an echo is equal to 18 seconds divided by 50. 18 seconds divided by 50. Therefore, we can say speed will be equal to total distance travelled 2d divided by time taken t, that is 2d we have calculated, which is equal to 120 meters, divided by time taken is 18 divided by 50. 18 by 50. Taking reciprocal and multiplying, we get 120 into 50 divided by 18. 6 into 3 is 18. 6 into 20 is 120. 220 into 50, you get 1000 divided by 3, which is equal to 333, approximately 333 meter per second. So 333 meters per second is the speed of sound. Okay. Problem 1. The wavelength of waves produced on the surface of water is 20 centimeter. If the wave velocity is 24 meter per second, calculate the number of waves produced in 1 second. The number of waves produced in 1 second is the frequency. The time in which one wave is produced, which is the time period. Now, how to find the frequency? If wave velocity and wavelength is known, here wavelength is lambda equal to 20 centimeter. Here it is in 20 centimeters, and the wave velocity V is given 24 meter per second. Since wave velocity is in meter per second, we have to convert this 20 centimeters into meters. We know 1 meter is 100 centimeter, which means 1 centimeter will be 1 by 100 meter, that is 10 raised to minus 2 meters. Okay, here we have 20 centimeter, then 20 centimeter will be 20 into 10 raised to minus 2 meters. Okay, that is 20 into 10 raised to minus 2 meters. Now we can find the frequency. We have wave velocity V is equal to lambda into frequency F. Here frequency F will be V divided by lambda. V is equal to 24 divided by lambda is 20 into 10 raised to minus 2. Okay, taking this 10 raised to minus 2 to the numerator, we get 24 into 10 raised to 2 divided by 20, which is 24 into 100 by 20. Cancelling zeros, we get here 2 and 24 can be cancelled. 12. 12 into 10, 120. So 120 hertz is the frequency. Now we can find time period. We have time period T is equal to 1 by frequency. We have calculated the frequency. Yes, that is 1 by 120, you will be getting 0.008 seconds. So this is the time period. We have calculated frequency and time period. Second problem, a man standing 48 meters away from a wall fires a gun. Calculate the time after which an echo is heard. The speed of sound in air is 320 meter per second. Here speed of sound is given, which is 320 meter per second. So here there is a person who is firing a gun, and this is a wall. Okay, so the sound will go hit this wall and return back. Only then it is a echo. Okay, here we are given speed v is equal to 320 meter per second. Okay, what is the total distance traveled? Distance traveled d. Given that a man standing 48 meter away from the wall. So this distance is 48 meter. So here the sound wave should go to this direction, touch the wall and come back. Okay, which means 2d we have to find. 2d means 2 into 48 meters. 2 into 48 meters, which is equal to 96 meters. Okay, 96 meters. So here we have v and d. We have to find the time. How to find time? We have speed is equal to distance by time, which means time is equal to distance divided by speed. Okay, so here we are taking 2d. The distance will be 2d. If this distance is taken as d, distance from the person to the wall is taken as d, then the total distance travelled will be equal to 2d and the speed of sound in the medium, which is v. So here 2 into 48, which we have already calculated, divided by 320, which is 96 divided by 320. 96 divided by 32 into 10, cancelling this becomes 3. 3 into 32 is 96. 3 divided by 10, you get 0.3 seconds. Unit is seconds. Unit of time is seconds. Okay, problem number 3. What should be the minimum distance between the source and reflector in water so that echo is heard distantly? The speed of sound in water is 1400 meter per second. Very simple question. Here we have to find the minimum distance between the source and reflector. So here if you have the source and this is where the reflector is, we have to find the distance between the source and reflector. That's the minimum distance, which is d. Okay, we have speed of sound in a given medium. V is equal to total distance travelled divided by time. Okay, here the speed of sound in water is given. Speed in water is 1400 meter per second. Okay, time. What will be the time? The minimum time is 0.1 seconds. Okay, only if the sound is 0.1 second, this echo or the reflected sound can be heard. Okay, we have to find what d is. Okay, d is the distance between the source and the reflector. 2d is the total distance that is travelled. We have v is equal to 2d divided by t. We need to find what d is, which means d will be equal to v into t divided by 2. Cross multiplying, we are taking t here and divided by 2. Okay, put the values. V is equal to 1400 into time, t is 0.1 divided by 2. That is 700 into 0.1, which is equal to 70 meter. So the distance between the source and the reflector will be, minimum distance should be 70 meters. Okay. Problem 4. A radar sends a signal to an aeroplane at a distance 300 km away with speed of 3 into 10 raised to 8 meter per second. After how much time is the signal received back after reflecting from the aeroplane? So here the distance between the radar and the aeroplane d is 300 kilometers. Distance is in kilometers and the speed is given in meter per second. So we will be converting this 300 kilometers to meters. 1 kilometer is 1000 meter. Therefore 300 kilometer will be 300 into 10 raised to 3 meters. Okay. Speed is given. V is equal to 3 into 10 raised to 8 meter per second. Okay. Now how to find time? We have V is equal to 2d divided by t. Then t is 2d divided by v. 2 into d is equal to 300 into 10 raised to 3 divided by v is equal to 3 into 10 raised to 8. Here we can write 2 into 3 is 6 into 10 raised to. Here we have 2 zeros, which means 10 raised to 5. 2 plus 3 is 5 divided by 3 into 10 raised to 8. 3 and 6 can be cancelled. We get 2 here. So 2 into 10 raised to minus 3 seconds. So this is the time. Okay, this is the how much time, after how much time is the signal received back After reflecting from the aeroplane, the time is 2 into 10 raised to minus 3 seconds. That's all for today. In today's class, we have discussed about the reflection of sound waves. We have studied about echo and solved problems related to it. Hope you all enjoyed the session. I'll be back in the next session. Until then, stay tuned to LearnoHub. LearnoHub free hai par best hai. Thank you.